So we continue our morning session, and the next speaker is Hirotaka Tashiro, and the title of his talk is Hasse norm theorem for three manifolds. You're welcome.
Nice to meet you. My name is Hirotaka Tashiro, who is a doctoral course student of Kyushu University. Thank you for inviting me to AGMA. My title is Hasse norm theorem for three manifolds. This talk is based on my paper in arXiv. First, as mentioned in the talk of Atsuki Kuramoto, arithmetic topology is the field which aims for mutual development between number theory and three-dimensional topology. M-square-KR dictionary is introduced by Barry Mazer, Masanori Morishita, Mikhail Kaplanov, and Alexander Rezinkov, which marshal the basic analogs of this. We introduce the notions used in this talk. There are analogies between an integer ring of a number field and a three-dimensional manifold, a prime ideal and a knot, a finite set of prime ideals and a link, a finite extension of number fields, and a finite covering of three-dimensional manifolds. Also, there are analogies between a periodic integer and a tubular neighborhood of K, a periodic field and a boundary torus of Vk. We call a loop of del Vk along K the longitude of K, and a loop of tangling for K like this figure, the meridian of K. Here, the coefficient of a chain group and a bound homology group is Z in this talk. There are analogies between a multiplicative group of F and a group of two chains of M, boundary maps. The boundary map of the arithmetic side is the map making the principal idea of a number, and topological analog is the map taking the boundary of two chains. There are analogies between an ideal class group of F and the first homology group of M, a unit group of OF and a second homology group of M. Based on analogies, I will talk about Hasse norm theorem. Next, arithmetic topology has a basic problem, which is what is a geometric analog for a three-manifold of the set of all prime ideals of a number ring. A candidate to answer this question was introduced by Nibo Ueki, which is a very admissible link. A very admissible link is defined as follows. Let M be an oriented connected closed three-manifold and L a link of M. L is a very admissible link if satisfies the following conditions. 1. L consists of countably many tame components. 2. For any finite coupling branched over a finite sublink, H1M is generated by components of F inverse L. By the following theorem, such a link exists in M. We fix one of very admissible link for M. We define the ideal group of M. There is the above sequence in number theory. This geometric analog is the below exact sequence. By the analogy, geometric ideal group is defined as follows. Let M be an oriented, connected, closed screen manifold endowed with a very admissible link. We denote by del K a boundary torus of K. Then, an ideal group is defined by the following formula. This formula means this element has only finite components that have the longitude of K. We construct the diagonal map, geometric diagonal map, delta M. Delta M is a map from a direct limit to an ideal group. Here, this direct limit is made of a direct system which consists of the family of H2ML and inclusion maps between them. Let L be a finite sublink of a very admissible link, and width XL is M minus L. Del L is a disjoint union of del K. Then we have the following sequence made of an excitation isomorphism and a boundary map of a relative homology sequence. Taking the limit with respect to L, we obtain delta M. We define by PM equal image delta M, the principal ideal group of M. So we state the Hasse norm theorem. In number theory, when let E over F be a finite cyclic extension of number fields, this equation holds. Hasse proved it in 1931. Next, we state the main theorem. Let M be an integer homology 3-sphere and a finite cyclic covering branch over finite sublink. Then F star is induced by F. And the following equation holds. Since it is trivial that the right side is included the left side by the below commutative diagram, we should prove that the left side is included the right side. We interpret the equation. An ideal group is the subgroup of a product of H1 del K. Let the lower right figure be a K component of an ideal group element. If this K component is what bound the purple disk AK, which is the lower left figure, and it is the link like the upper right figure in a covering space. Then there exists the red disk AK1 and the blue disk AK2 such that this diagram is commutative. So this is the claim of the equation. We introduce the outline of the proof of the Hasse norm theorem. As previously mentioned, the right side is included the left side. We observe the left side is included the right side. Take any element F star A of the left side. Using the relation between a homology group and an ideal group and the exact sequence with respect to cyclic couplings, we have this equation. By an explicit description of delta M, F star U equals 0. Thus, F star A is the element of the right side. And what is the key ingredient of the proof? It is the explicit description of delta M. Let M be an integer homology 3-sphere and L a finite sublink of a very admissible link. Then we have the following exact sequence. Hence, H1L and H2ML are isomorphic, and H2ML is generated by Seifert surfaces of the component K of L. By using the excision isomorphism and the boundary of the relative homology sequence, we obtain the following sequence. Next, we consider what is the shape of AK, and the boundary of AK becomes this excision remove int real from M. So SK is punctured the holes of int real. This punctured surface is an AK as follows. This figure describes generators AK1 and AK2 when M equal S3, L equal K1 cap K2. We bound AK1. The outside loop is the longitude of K1. The inside loop is the meridian of K2 and the inverse orientation of the longitude. Therefore, we can denote del as follows. Del Sk is generated by the longitude of K and the meridian of K prime. The coefficients of the meridians means how many K is tangled with K prime. So their linking number of K and K prime. Taking the limit with respect to L, we obtain the explicit description of delta M. In conclusion, the analysis between a finite cyclic extension and a finite cyclic coupling, a norm map, and an idyllic homomorphism, a norm map, and a principal idyllic homomorphism, Hasse theorem. Finally, we state future prospects. 1. This main theorem holds when M is an integer homology 3-sphere. When M is a general-oriented connected closed 3-manifold, does it hold the Hasse theorem? 2. Are there examples for which the Hasse theorem doesn't hold? 3. Can we construct necessary and sufficient conditions to hold the Hasse theorem? In other words, can we construct a geometric analogy of a Shapirevich state group of an algebraic torus? This is all for my talk. Thank you for listening.
Thank you very much.